Welcome to Physics 30 Prep Fast Track. We're looking at lesson 3.3, Work and Energy. So when an applied force, Fa, is exerted on a mass over a distance, so you're pushing on an object or pulling on an object and that object moves a certain distance, then we say that work is done on that object. And the formula for that is work is equal to Fd. Now, we add the Fd, we add cos theta to it because generally the direction that you apply a force might be to the right, and of course the displacement of the object might also be to the right. And since in this case they're both in the same direction, the angle between them is 0. And because the angle is 0, then the cosine of 0 is 1, and 1 times any number gives you that number. So Fd times 1 would just be Fd. So when they're both in the same direction, then we don't worry about the angle. But if you were out on the skating rink and you were pulling a small child in a sled, then you might pull on the rope in this direction. And so the sled would move to the right, but your force would be at an angle. And because it's at an angle, then we have to determine what that angle is, and that's when the work done is a combination of the force and the distance multiplied, but the angle between them also has to be taken into account. So once in a while you'll see that we need to use just Fd, and sometimes we'll have to use Fd cos theta. So, continuing, the work done on the object is the result of a transfer of energy. Whenever work is done, energy is transferred. And you can get all kinds of different types of energy. One type of energy that you might give to an object as you do work on it, or as you apply a force over a distance, is kinetic energy. And kinetic energy is called the energy of motion. And the formula for kinetic energy that we'll look at a little bit later is 1/2 mv squared. And notice that it's the mass and the speed of the object that give it its kinetic energy. Potential energy is called the energy of position. And when we talk about gravitational potential energy, we say it's mass times gravity, which of course is its weight, times the height. So the higher the object, the more potential energy it has. You can also raise the temperature of an object or the surrounding air due to work against friction. Anytime you rub two things together, you're applying a force over a distance, and the work energy that you do sometimes can be used to warm up your hands, or as an object falls through the air, it rubs against the air molecules, heating them up. And so there's a number of different ways to express heat energy. In chemistry you might see delta H. I call it the work done against friction, and that's equal to the force of friction times d. So that's a good little equation. And of course the energy of an object will not change unless work is done on it. So looking a little more closely at kinetic energy, it's, as I said, the energy of motion. The faster an object moves, the more kinetic energy it has. And we say the formula for kinetic energy is 1/2 mv squared. So when you throw a ball, the initial kinetic energy, as you reach your hand back and get ready to throw, the ball is stationary in your hand. And then you apply a force over a distance, and your arm does the work. And of course, force over a distance is work. The energy from you, sort of a biomechanical type of energy from the cornflakes you ate this morning, turns into kinetic energy of the ball and gives it more velocity. And there is an easy derivation of this formula. We take it from the definition of work from the previous page, and we say that, of course, work is equal to Fd, and that's equal to MAD. But we also know that in kinematics we had an equation that said that Vf squared was equal to Vi squared. That is the initial velocity before you let go of the ball, or before you start accelerating the ball. It has a certain velocity, Vi is 0. And then, of course, as you accelerate the ball over a distance, and you can see that right here, that gives you a final velocity. You're accelerating, you're adding energy. And so the work formula and the kinematic expression that we use here, they are tied together. And when you do tie them together, you can just manipulate the formula by making both ADs here the same, and you end up eventually with the work, or the change in kinetic energy, is 1/2 mv squared. It's a nice little derivation. So we're not just pulling an equation out of a hat, we're actually using a couple of concepts to derive this equation. So you know that this equation is valid and it works very well. Now, the other type of energy that we often convert our work into is potential energy. Potential energy is the energy of position. The higher an object, the more gravitational potential energy it has. And we have a simple formula for potential energy. It's of course just equal to F times D. And of course the F, when you're lifting an object against gravity, the force, or F, is the force that you apply upward to raise an object against its weight. And its weight is mg, mass of the object times gravity 9.81. And then of course, so that's F. And of course then we also have h, well the change in height. Height is just distance. Alright, so you get FD, and its EP is equal to mgh. And there are lots of forms of potential energy. Another form is elastic. When you pull back on an elastic band on your finger, or you stretch as in the diagram, you stretch an elastic to put on your ponytail. And of course, initially the elastic has low potential energy. That is elastic potential energy. And as you stretch it, of course, you're applying a force over a distance. And so you're giving that elastic potential energy. And of course, it could then, when you release it, it could turn into kinetic, or you could send it into the air. In the case, it would turn into gravitational potential. So lots of different types of energy. And of course, there's kinetic, as we discussed earlier. There's gravitational potential, and there's also elastic potential right here. All right, so releasing a stretched elastic band will result in kinetic or gravitational potential energies, and of course can be dangerous. All right, other forms of potential energy are chemical and electrical. So when you plug in your light, of course, or let's say you have a flashlight with a battery in it. Inside that battery is stored chemical potential energy, and of course when you turn on the switch, that potential energy turns into another form of energy, such as light and possibly a little bit of heat. So potential energies, there's lots of different types. Mostly in physics 20 we worry about gravitational, and occasionally we bring in elastic, but we don't deal with chemical or electrical in this course. So we've learned a little bit about kinetic energy and gravitational potential energy. They are known together as mechanical energy. And in an ideal situation where there is no friction, the mechanical energy of a system is constant. Of course, when you have something like friction, then you might start off with a whole bunch of potential energy, but as it loses it to friction, it may lose some of its mechanical energy, because not all of its potential is turned into kinetic. So here's an example of conservation of energy. Pendulum, of course, has high points and low points in its trip as it goes from left to right. So here it is at the bottom. That's called the equilibrium level, and that's where, as it's moving back and forth, it would have zero potential but lots of kinetic energy. At this point over here, it would have lots of potential because of its height, but it would have a very low amount of kinetic. In fact, it would stop here, so it would have zero kinetic. So at point number 1, you have lots of kinetic energy. At point number 2, you have lots of potential energy. And of course, as the pendulum swings back and forth, there's a constant conversion of one type of energy to the other. But the thing is, if there were no friction, then you would have the total mechanical energy would always be the same. On the left, low EP, high EK. On the right, low kinetic, high potential. And we go through this argument. On the left, the object is moving through the equilibrium position. On the right, the mass is stopped at the highest point. And so, if no energy was lost, the system would oscillate back and forth indefinitely. But of course, there's no such thing, really, as an ideal or perfect system. But we can use that concept to help us to understand conservation of mechanical energy. And it helps us to try to reach an ideal, such as superconductors reduce friction so much that you can almost say it's negligible. And in that case, you then have almost a perfect system. So that's a quick overview of mechanical energy, that is potential energy, kinetic energy, and of course the work that you do to an object to give you that type of energy. So the next lesson will deal with power, and then the lesson after that will deal with some examples of putting these concepts together mathematically, equating kinetic and potential energies at different points along an object's path.